let's just remind ourselves of the conditions we're going to have. So these conditions, you can think of this as being the ultimate law. So these conditions cannot be broken. If they are broken, you cannot apply what we're going to do now. So the conditions are that the motion is in a straight line, and that the acceleration is constant. If this does not hold, we cannot apply these equations. So the first thing to note is, if the acceleration is constant in time, remember it means its value does not change as time increases. So its value at this instant is equals to that. Its value at this instant is equals to that. And on average, if I take the average over any time interval, I will just get the same value. So for constant acceleration, I have that the average acceleration is equals to the instantaneous acceleration. You can only say that if the acceleration is constant. Now this already gives us one equation that we can work with. If we look at how we defined average acceleration, we said this is equals to our change in velocity over a change in time. Now I'm just going to assume that our initial time was 0, just so that I can cancel it out. It doesn't have to be like this. You can put any value in there and just substitute in delta t. But we just said that if the acceleration is constant, this is equal to the instantaneous acceleration. So I can write that as the instantaneous acceleration. I'm just going to write regular a for that. So I've got this equation. A is equals to final velocity minus our initial velocity divided by a time. And we can solve for the initial velocity. We multiply by time, and we add a v initial both sides. And what we get is we can calculate the final velocity if we know the initial velocity and the acceleration and how long it takes to reach that velocity. So if I know how fast I'm going at time equals 0, I know the acceleration, which is constant, and I want to figure out how fast am I moving at some later time, I can use this equation to get that quantity. So this already tells you if you do an experiment, if you just have a stopwatch and you know how to measure velocity at one instant, you know acceleration, you can calculate final velocity. Now, this is the first equation of motion that we're going to derive. The second one follows from the following principle. This is time in terms of seconds. This is now velocity. Let's now just look at a special case where I've got a constant average velocity. A constant average velocity. So at any point on this axis, at any point in time, I've got exactly the same velocity always and ever. So if I average the velocity over this time interval, I would just get the same value as I've got there and there. Now, what quantity do you think will be given by this area? Does it have any physical meaning for us? Displacement. Why do you say displacement? Is it taught in school, or is it can you tell me why? Okay, so if you're saying if I calculate the area there, I have to multiply. So this area will be equals to, let's say that's our final velocity. Let's just say that's 0. Oh, sorry, that's our average velocity, sorry. Or constant velocity. So this area is equals to that, so which is our average velocity, times this, which is the time interval, And we know that our average velocity is defined as a displacement divided by time, which means displacement is equals to average velocity times the time. So these two things look a lot similar. So therefore that area is equals to the displacement that happened over that time. But the thing we're not always going to be so fortunate to have a constant velocity. We can have a velocity that changes. Let's say we take away a little bit of this area and we add it on over there. So we take away the triangular area equals to that, and we add it on over there. And this corresponds then to a constant velocity. Oh, sorry, a linear velocity. So it's the velocity increases linearly with time. So what I've taken away over there, I've added on over there. So the area underneath the curve remains the same. So let's calculate the area now for the case where we've got velocity changing linearly with time. The area now will be equals to that rectangle. So let's just call this our initial velocity. So it will be equals to our initial velocity times the time interval plus the area of that big triangle. Now if we call that our final velocity, so that's t final, that's t initial, the area of this triangle is equals to a half times the base, which is delta t, times the height. So the height is this value, v final, minus this value, v initial. So the height is v final minus v initial. So I've got v initial times delta t plus a half delta t times v final minus a half v initial times delta t. So 1 minus a half gives me just a half. I can write this as v final plus v initial times delta t. Remember, the area has remained the same, so I've already got an expression for the area over there. So I can substitute this in. This gives me the average velocity divided by delta t. If I cancel out the delta t's, I get my result, which is quite simply that the average velocity between any 2 points in time is equals to a half of what the velocity was at the end of the time interval plus what the velocity was at the beginning of the time interval. Right, so if I've got constant acceleration, I can relate the average velocity to the velocity at 2 time intervals through this relationship. And now if we just take this equation and we substitute it in to our equation for the average velocity, so we can relate this to, remember this is going to be our change in position over the time interval. We can now get a second equation of motion, which I'm going to show you on the slide.